Something happened on the morning of December 11th that no one expected. Just after passing Mars, 3I Atlas suddenly tore away nearly half its tail. For hours, the comet's ion stream warped, split, and then vanished, like a ribbon caught in a quiet solar storm. But then came something even stranger. Telescopes began detecting a fluctuation not in the comet, but in the sun itself. What followed was a cascade of data no model had prepared for, and now scientists are circling one question they can't seem to release. If 3I Atlas is only a comet, why does the sun look hurt? Stay with me. This isn't science fiction. It's solar physics, being rewritten in real time. 3I Atlas reached a critical point in its outbound path, crossing the orbital track of Mars. By every conventional model, this moment should have been routine. The object had passed perihelion weeks earlier, survived its harsh brush with sunlight, and was now coasting outward. By this stage, activity should have been fading. The tail, mostly ions and volatile gases, should have thinned and softened. Instead, astronomers witnessed something no one predicted: a sudden fracture in the ion tail. It began as a visual anomaly captured almost simultaneously by telescopes in Arizona, Chile, and the Canary Islands. What had been a smooth, continuous stream of charged particles split in two, not gradually, not like a comet dimming over time. This was abrupt, like a fault line snapping in open space. The separation was sharp, jagged, long, a disconnection event in the language of heliophysics, but one that refused the usual script. To understand why it matters, it helps to remember how a comet tail forms. As a comet approaches the sun, radiation and solar wind ionize gases rising off the surface. Those ions are swept away, forming a tail that always points away from the sun. It can stretch millions of kilometers, and it usually evolves slowly as the comet moves. But what happened with 3I Atlas wasn't gentle evolution. It was rupture. The fracture was recorded across multiple wavelengths. Invisible light. It looked like a sudden bend, a kink in the tail's spine. In ultraviolet, the region behind the nucleus showed a gap, an actual absence where flow had been. But the most telling data came from radio and spectral imaging. Instruments detected a change in ion density that was abrupt and uneven. On one side of the break, the tail remained thin, wispy, dispersing. On the other, it was gone entirely, as if something had sliced through it and let one half drift away. This wasn't minor. It was a large-scale collapse in the tail's architecture. Theories began circulating quickly. Was it a solar wind anomaly? A collision? A transient electromagnetic pulse? None fit cleanly. Solar wind at that moment was relatively steady. No flare had erupted in the preceding hour. No known object was close enough to interfere with the comet's path, and the scale of the disconnection only deepened the puzzle. Based on time delays between observatories, scientists estimated the break extended for tens of thousands of kilometers in under 15 minutes. That kind of structural shift isn't typical of passive outgassing. It looked mechanical. It looked intentional. Even more confusing was what didn't happen. The comet's core remained completely unaffected. Its brightness stayed stable. Its trajectory showed no wobble. If internal stress or nucleus instability caused the break, you'd expect changes in rotation or mass loss. There were none. The separation looked clean. Too clean. Like a system shutting off a function it no longer needed. For observers watching in real time, the scene felt surreal. A massive interstellar visitor had shed a major component of its structure with no warning and no obvious trigger. And yet it did so without losing stability. The comet kept moving, calm and unfazed, as if nothing had happened. The moment 3I Atlas crossed Mars's orbit, something else crossed a line. 2. Our understanding of what this object is. A comet doesn't usually seem to choose to discard part of itself. But that morning, that's what it resembled. And in the minutes that followed, the story turned stranger still. In the hours after the tail fracture, something unexpected happened in the solar wind. As the object moved outward beyond Mars, solar observatories noticed an invisible ripple spreading through the heliosphere. Not a visible flare, not a magnetic storm, a density wave, subtle, real, moving with almost surgical precision. Later, scientists would call it a shock line, and its timing was too perfect to ignore. The solar wind is a continuous stream of charged particles, mostly electrons and protons, flowing out from the sun in every direction. It's chaotic, turbulent, influenced by sunspots and coronal mass ejections. Normally, when something like a comet passes through it, the interaction is predictable. The object disturbs the stream, mild and irregular, like a stone disturbing water. But what happened on December 11th wasn't mild, and it wasn't irregular. At approximately 0640 UTC, the Parker Solar Probe, in its outbound arc, detected a sudden spike in particle density. The probe had been monitoring a calm patch of solar space, smooth field lines, steady flux. Then, without warning, a compression wave passed through, a sharp front of elevated plasma pressure. The magnetic field twisted, particle counts briefly doubled, and the solar wind slowed just enough to register across multiple instruments. Minutes later, that same ripple was picked up by ESA's solar orbiter, positioned farther out along the ecliptic. What caught scientists off guard wasn't only the shock's presence, but its direction. It was moving away from the sun, yet not as part of any solar event. Tracing it backward pointed to a single origin in space, the position of 3I Atlas. There had been no flare, no coronal mass ejection, no solar change to justify a pulse like this. And yet there it was, a crisp pressure line aligned perfectly with the comet's path, as though cast outward from the object itself. The data raised immediate red flags. A shock line implies an interruption in plasma flow, pressure rising sharply, forcing particles to compress, bounce, and redirect. Usually, that happens when solar material strikes something dense, a planet's magnetosphere, or a spacecraft hull. But 3I Atlas has no magnetosphere, no magnetic shielding, no thick atmosphere, no known surface field strong enough to generate resistance like that, which led to a question still hanging in the dark. What did the solar wind hit? Some suggested the tail fracture released a sheet of highly charged particles, a cloud dense enough to cause compression, but that wouldn't explain the wave's clean profile. Others argued the object discharged something, ionized gas or plasma that briefly behaved like a reflective surface. Yet the data showed no lingering halo, no sustained field. The most provocative idea came from a small team at the Max Planck Institute. Using simulations, they proposed the shape and material of 3I Atlas might have temporarily created a conductive cavity in space, a floating shield. Not magnetic, but reactive to solar plasma. If the object shared a reflective layer, perhaps the fractured tail was more than a trail. It could have formed a microbubble in the solar wind, and when that bubble collapsed, it could trigger the shock line the probes detected. The theory remains speculative, but it fits the timeline. The tail fractured first. The density spike followed within minutes, and the shock line moved not from the sun, but outward, like a pulse responding to loss. What it means is still unclear, but one thing is certain. On December 11th, the solar wind recorded an impact with something it didn't expect. Not a planet, not a flare, something else, traveling in silence, shedding pieces of itself like signals, while earthbound telescopes analyzed the tail's aftermath. A separate observation from deep space sent a tremor through astrophysics. At approximately 0702 UTC on December 11th, a brief, unmistakable bright flash was recorded by ESA's solar orbiter. It appeared in ultraviolet imaging for less than 5 seconds. But what stood out wasn't the duration, it was the location. The flash originated precisely at the coordinates of 3I Atlas, just beyond Mars's orbit. At first, it was flagged as a possible sensor glitch. Spaceborne observatories regularly suffer cosmic interference, radiation spikes, thermal artifacts, brief misreads from high-energy particles. But this flash didn't behave like an error. It followed the outline of a real object. It had gradient structure. It drifted subtly with the comet's own trajectory. ESA scientists reran calibrations. They checked for flares, particle storms, software hiccups. Nothing abnormal surfaced. More importantly, two other instruments, onboard spectrography and heliospheric imaging, captured matching anomalies within seconds. The ultraviolet flash wasn't phantom. It was real and centered on 3I Atlas. In the images, it appeared as a sharp, irregular burst, a radiant bloom erupting from the side of the object. Not from the tail, not from solar backscatter. From the nuclear region itself, it wasn't round, not diffuse like reflected sunlight. It was shaped, lopsided, layered, almost geometric. The radiance emerged from a single point and expanded into an uneven halo before vanishing into the void. It happened so fast no follow-up frame captured its evolution. But the imaging array revealed one detail that mattered. The flash preceded a minor shift in solar plasma density, measured moments later by Parker Solar Probe. That order matters. It suggests the event wasn't caused by an external solar interaction. It initiated something, and the solar wind reacted afterward. Speculation rose quickly. Was it a volcanic-style outburst? A sudden venting of pressurized material from deep within the body? Rare. Yes, but not impossible for a volatile-rich object. Yet if that were true, spectrometers should have seen spikes in carbon monoxide, carbon dioxide, or hydroxyl emissions. Instead, the spectrum following the flash went flat. No chemicals, no gas, no particulate trail, just a burst of light. That absence became the story. One possibility, raised quietly in internal notes, was electroluminescence, light emitted by a high-voltage discharge. We've seen it in Earth-based plasma experiments, and in lightning, but never in a comet. For it to occur, the object would need to store charge potential and release it as a sudden arc. In vacuum, that becomes stranger still. Could 3I Atlas contain internal charge storage? Could the tail fracture destabilize a field that then discharged through the surface? The idea remains speculative, but ESA polarization logs lean in its direction. For minutes before the flash, the object showed anomalous reflection angles, as if surface alignment was shifting unnaturally. A few degrees at first, then more, then the flash. Almost like realignment followed by ignition. The most unnerving hypothesis from one analyst was simple. The flash wasn't an accident. It was a response, a trigger, a consequence of the detachment. Perhaps a brief energetic signal, visible, timed, decisive. Whatever it was, ESA's bright flash became a central point in the December 11th timeline. This wasn't a comet crumbling. It wasn't sunlight glancing off ice. It was something else, brief, bright, and final, and it marked the beginning of a deeper shift in how we would see this object, not just as a visitor from another star, but as a presence capable of reacting. While eyes stayed on 3I Atlas and the strange flash, something else unfolded quietly at the heart of our solar system. On December 11th, one of the Sun's most active regions, Artretusen, Fem, 100 Retten, entered a volatile phase. Solar astronomers had tracked it for days. Large, magnetically twisted, unstable at the edges. Multiple observatories predicted a jet event. But when the coronal jets finally fired, their trajectory stopped scientists cold. The Sun had missed. Typically, solar jets, narrow bursts of superheated plasma, erupt along magnetic field lines. Following predictable arcs, Their direction is governed by loops, not aim. And yet, on December 11th, two separate jets ejected from AR-3513 and curved sharply away from the expected angle, not toward Earth, not toward any obvious body, laterally, as if something had distorted the field itself. At first, the deviation looked minor, only a few degrees, but when the Solar Dynamics Observatory overlaid projections against prior models, the mismatch became impossible to dismiss. The magnetic lines had warped, not from within, but from influence outside the solar surface. The field looked like it buckled around an invisible boundary, and the timing aligned precisely with the tail fracture and flash near 3I Atlas. To be clear, the Sun doesn't target anything. Its emissions follow internal magnetic structures shaped by plasma motion. When jets misalign, it's usually rotation, subsurface shifts, or model error. But this time those explanations didn't hold. The models had been right. AR-3513 behaved as expected until the exact moment 3I Atlas destabilized its tail beyond Mars's orbit. The question emerged softly, then louder. Did something between the Sun and 3I Atlas redirect the jets, or more unsettling, did the object's presence alter local field geometry near the Sun? ESA's solar orbiter added more. Its heliospheric imager caught faint bending in plasma density lines only on the side facing 3I Atlas for roughly 20 minutes after the jets fired. The local solar wind stream showed lateral drift, a slow, unnatural push outward, like a curtain being drawn. It matched no catalogued phenomenon, no flare, no CME, no collapsing loop. Some theorized a temporary flux rope, a cylindrical twist of magnetic fields forming in the space between the comet and the Sun. But there's no known mechanism for a comet to generate that, especially at that distance. Others suggested the tail separation discharged unusually conductive material, interfering with the heliospheric current sheet. Still, it didn't fully explain the jet's shape or the sudden distortion of field lines on the Sun itself. One solar physicist asked what no one wanted to answer. What if the jets missed because they were pushed not by wind, not by mass, by influence, as if something briefly rewired the electromagnetic architecture at the Sun's surface? The Sun isn't aware, but its field is responsive, and whatever happened on December 11th made it respond like a living organism, adjusting to unexpected pressure. The jets that should have followed their arc didn't. Their paths curled outward and weakened. Energy that should have held its velocity dispersed. And somewhere along that bent trajectory, billions of kilometers from the Sun, drifted a lone interstellar object, missing half its tail, pulsing with silence. What had it done, or maybe more accurately, what had it just absorbed by mid-morning December 11th? What began as a curious anomaly, the sudden fracture of 3I Atlas's tail, started to look like one piece of something larger. The timeline was the key. One event followed another with uncanny precision. The tail fractured. A bright flash bloomed at the core. The solar wind reacted. And then, just when things should have settled, the Sun flared. It wasn't massive, barely an M-class event, but it was surgical in timing. It erupted from AR-3513, the same region that had fired the misaligned jets. The flare began at 0706 UTC, exactly 4 minutes after the tail rupture. When NASA and ESA teams overlaid heliophysical data with 3I Atlas's trajectory, something became unmistakable. The flare vector pointed toward the region of space where the comet had just ejected half its tail. Solar flares are usually treated as random in their precise timing. They follow cycles, yes, and emerge from active regions. But they don't aim. They don't synchronize. This flare behaved differently. It aligned. It fired along a clean, angular path, the same path where the tail disconnection occurred. Solar physicists noticed another disturbing detail. The flare wasn't preceded by the usual chaotic buildup. Most flares rise from a storm of magnetic tension, twisting, churning, pressure accumulating over time. But AR-3513 had been stable for hours. Its last emission had been nearly 20 hours earlier. It wasn't supposed to erupt again for at least a day, until it did. A simulation from the University of Colorado's space weather team offered a clue. When they introduced a hypothetical plasma void, a zone where charged material was suddenly removed, the flare behavior matched, and that's exactly what the tail loss could have created. A sudden vacuum of ionized mass, freshly stripped, plus a drift in solar wind. But it wasn't only direction. It was sequence. 0658 UTC, tail disconnection. 0702 UTC, bright flash. Compression shock in the wind, then the flare. 5 events, about 11 minutes, all anchored to one object that shouldn't be active anymore. The idea that a comet could trigger a solar flare sounds absurd at first. The mass difference is immense. The Sun outweighs Earth by 330. 000 times. A comet is dust by comparison. But some began to ask a different question. What if it didn't cause the flare, but coordinated with it? Theories rose like heat. Could the tail loss discharge enough charge to collapse local plasma gradients, destabilizing magnetic reconnection? Could it release conductive particles that catalyze field line snapping? Could the object's internal structure store, amplify, or redistribute energy gathered from solar pressure? Or simplest of all, did the comet know the flare was coming? Some physicists remained skeptical, warning against assigning agency. Yet others pointed to the precision, the symmetry, the clean detachment. It wasn't only that a flare happened, it was when it happened. And in astrophysics, timing is everything. Minutes after the flare aligned with the fractured tail, something unexpected began to appear in the light. Not visible light, but polarized light. Filtered and structured. At first it was subtle, a gentle curve in solar reflection angles. Then, over 20 minutes, the signature sharpened. Across 3 observatories, the same result appeared. The polarization signature around 3I Atlas had flipped. Polarization is one of the most revealing and most delicate tools we have. It tells us how light scatters off surfaces, dust, ice, gas, atmosphere, when sunlight reflects off rough surfaces like comet dust. Scattering is chaotic and diffuse. Polarization tends to be low, soft, smeared, but when light reflects off something smooth, metallic, or geometrically consistent, the signal becomes directional, and when it flips, it usually means either the surface orientation changed dramatically, or the nature of the surface changed. On the morning of December 11th, ESA's polarimetric imager detected a deepening trough around 3I Atlas, where the expected pattern should dip gently and return as the object rotated. The dip became abrupt and reversed. The polarization vector turned positive and stayed there longer than expected. That is rare. Only a handful of comets have shown similar behavior, and none were interstellar. To a trained eye, it meant one thing: a smooth, specular reflection had emerged. In plain terms, it began reflecting sunlight like a mirror. But comets don't reflect like mirrors. They're porous, jagged, chaotic. Their surfaces scatter light like fog, diffuse and messy. A polarization flip like this suggests something structured and aligned has either been exposed or activated. And then analysts noticed something even stranger. The flip coincided exactly with the flare burst from AR-3513. The Sun emitted a focused pulse. Seconds later, 3I Atlas's polarization signature changed, not in one band, but across ultraviolet, visible, and near-infrared. A team in Japan ran simulations and proposed a chilling possibility. The object altered its surface characteristics in real time, rotating, shifting, or unfolding something that changed its optical properties. At the Max Planck Institute, polarization experts noted the inversion angle had narrowed. That typically happens when a scattering surface becomes more uniform. In technical terms, the object went from behaving like a dusty snowball to something closer to a polished, elongated panel. Had the object rotated a structured surface into view, had the tail loss exposed something beneath, a plate, a shield, a segment built to catch light and redirect it, if true, it wouldn't be the first interstellar visitor to hint at anomalous polarization. Oumuamua showed faint signs in 2017, but nothing this dramatic, and nothing timed with solar events. By late morning December 11th, researchers began referring to the change as the mirror phase. A comet that lost half its tail, endured a synchronized solar flare, and now reflected sunlight as if it had switched modes. Skeptics suggested exotic ice or dust properties. Maybe carbon-rich material had been exposed. Maybe a crystallized shell lay beneath. But that still didn't explain the clean vector change or its timing. When polarization flips, it tells a story. And the story 3I Atlas seemed to tell was simple. It had revealed a new face. By mid-morning, radio telescopes tracking it reported something else they hadn't seen before. The object's Doppler profiles began to break down. Profiles used to measure particle velocities in outflowing gas and dust distorted, then vanished. What should have been a steady stream of measurable motion dissolved into static. The signal collapsed. To understand why that matters, remember how Doppler spectroscopy works in space. When gas and dust escape a comet, those particles move fast, sometimes several kilometers per second. They scatter light, and that light shifts depending on whether particles move toward or away from us. That shift, the Doppler effect, lets scientists chart tail behavior, shape, speed, dispersion. In an active comet, these profiles are crisp. You see peaks for water vapor, carbon dioxide, dust, rising and falling as jets fire and particles drift, even during disruptions like tail fractures. Doppler profiles usually spike. They don't disappear, but 3I Atlas did something else entirely. Around 0718 UTC, minutes after the polarization flip, facilities in Chile and Hawaii reported inconsistent ion tail data. Then the Green Bank telescope confirmed it. The signal wasn't weakening gradually. It was collapsing all at once. Velocity profiles from hydroxyl radicals to carbon monoxide lines lost coherence. Systems that had tracked particle speed for weeks suddenly showed nothing but noise. The tail hadn't just detached. It had gone silent. That disturbed analysts deeply. In a natural comet, detached tail material continues emitting radiation for hours, even days. Dust doesn't vanish. Ions don't stop moving. If anything, breakup should create more signal, not less. Theories poured in. Maybe the ejected tail dispersed so fast it fell below detection thresholds, but that would require speeds 10 times higher than observed. Others blamed interference from the recent flare. But nearby comets remained readable. The flare had passed, and still the tail stayed quiet. Then came a third idea, harder to ignore. What if the tail wasn't dispersing, but being reabsorbed, neutralized? In laboratory plasma physics, under certain electromagnetic conditions, a charge stream can be flattened by encountering opposing charge regions. In other words, the comet might have crossed an invisible boundary where particle signatures get erased from detection. That possibility gained weight when Japan's Nobuyama Radio Observatory detected a faint wideband flattening of signal-to-noise in the same region. Not only was there no Doppler signal, there was also no thermal noise from the missing tail. It hadn't just stopped emitting, it had stopped interacting with space entirely. Whatever the cause, the implications were serious. The Doppler profiles weren't merely silent, they were cut off. Like a live feed abruptly terminated, they remained offline for nearly 3 hours. During that time, 3I Atlas maintained its trajectory, brightness, and mirror-like signature. But the expelled particles, The breadcrumb trail we expected was simply gone. The collapse of Doppler data marked another turning point, because if the object wasn't ejecting anything anymore, then maybe it never needed to. As scientists scrambled to explain the silence, another anomaly appeared visible even to amateur astronomers. At precisely 0804 UTC on December 11th, observers across 3 continents captured something that shouldn't have existed. A briefly formed anti-tail on 3I Atlas. Not an illusion, not a processing artifact. A real, structured spike of material that appeared to stretch backward toward the sun. In comet science, anti-tails are real, but exceedingly rare, and they require very specific viewing geometry. Usually, an anti-tail is a trick of perspective. Earth crosses the comet's orbital plane, and for a short time, we look directly into a thin sheet of older dust, spread out ahead of the comet, along its orbit. From our vantage point, it looked like the tail was pointing the wrong way, toward the sun, instead of away. But 3I Atlas's anti-tail wasn't a trick. It wasn't a planar effect, or a simple illusion of orbital geometry. It was confirmed from multiple locations on Earth, with different viewing angles, and even more unsettling, it wasn't made of dust. It was ionized, with narrowband filters tuned to sodium and hydroxyl emissions. Researchers verified the spike came from freshly released material, not old debris from an earlier pass. And it didn't bloom outward in a fan. It stayed focused, narrow, dense, aligned straight along the solar vector. That single detail fractures what we think we know about comet behavior. Solar radiation and solar wind push ion tails away from the sun. That's comet physics 101. Material doesn't travel sunward without an external force. And yet, for nearly 36 minutes, 3I Atlas was expelling something that did. ESA's solar orbiter caught a partial view, just enough to make the silence feel heavier. The heliospheric imager recorded a filament of bright plasma racing inward, not diffusing, not bending, accelerating sunward in an almost straight line. Then, as suddenly as it arrived, the anti-tail collapsed. By 0841 UTC, it had faded completely. No comet on record has produced a sun-facing jet like that, especially not one made of ionized gas. The only remotely comparable case is a sunward-pointing jet seen in comet Encke in 2007. But that event was driven by extreme solar wind shearing during a coronal mass ejection, not by the comet itself. With 3I Atlas, the solar environment had been quiet for nearly an hour. No flare, no CME, no shock front to explain a forced reversal. So what caused the anti-tail? Some proposed a sudden inward-facing collapse of a magnetic structure within the coma. If the object carried localized charge and had just lost a massive component, like half its tail, the shift could have briefly carved a magneto-hydrodynamic channel, guiding charged material inward until the field snapped shut. But that remains highly speculative. It's a mechanism never observed in the wild, only hinted at inside controlled plasma labs on Earth. Others, more cautiously, began whispering a different possibility. Directed mass ejection. Not random venting, not passive chemistry. A sunward release, designed to create backward momentum. A maneuver borrowed from propulsion science. That interpretation gained weight when a slight change appeared in radial velocity right after the anti-tail vanished. The comet didn't swerve dramatically, but its reflective vector shifted by a measurable fraction of a degree. A tiny nudge, like a deliberate correction. Whatever the anti-tail was, it didn't behave like an accident. It behaved like a system, brief, controlled, purposeful. And after it ended, the surrounding space went back to normal. But nobody who watched that sun-facing stream forgot the shape of it. A comet doesn't aim at the sun, yet for 36 minutes on December 11th, 3I Atlas seemed to do exactly that, and just when it felt like the anomalies couldn't stack any higher, the object's brightness surged. The surge came after the fracture, after the polarization flip, and immediately after the anti-tail collapsed. At 0845 UTC, ground-based observers reported the comet's visual magnitude jumped by nearly an entire order. Amateurs in Italy, Chile, and South Africa noticed it within minutes, independently, under clear skies. They were using mid-range aperture telescopes. No heavy processing, no elaborate stacking required. The comet had simply brightened, visibly, unmistakably. But it wasn't a flare in the traditional comet sense. A normal flare comes from volatile ice sublimating fast, throwing gas and dust outward in a burst. When that happens, the coma grows, a diffused glow expands, the visible profile broadens. But with 3I Atlas, there was no coma growth, no swelling halo, no measurable rise in outgassing. Instead, the core sharpened, brightened, concentrating light rather than dispersing it. To observers, it was as if the nucleus polished itself mid-flight. Hubble wasn't positioned to catch the peak, but Pan-STARRS in Hawaii, sweeping the region for an unrelated session, caught the object minutes afterward. By then the brightness had stabilized, holding steady, no longer climbing, like a cycle completing and locking into place. The event raised two immediate questions. First, what caused the brightness spike without any thermal surge or volatile activity? Second, why didn't the brightness decay, the way a transient flare-up usually does? Under ordinary physics, an interstellar object moving away from the Sun at this stage should be fading. Its effective reflective area should shrink as dust disperses. Solar flux is declining. In plain terms, it should be slipping out of view. But 3I Atlas refused. When polarization data from earlier that morning was cross-referenced with the brightness readings, a clean correlation emerged. The surge began moments after the anti-tail collapsed, and exactly as the polarization vector settled into its flipped state. That implied the surface had become more uniformly reflective, and it did so in seconds. Spectral data showed an unusually flat albedo curve consistent with specular reflection, not diffuse emission. In other words, it wasn't glowing, it was reflecting, cleanly, precisely, efficiently. That kind of behavior suggests a smooth geometry, not a chaotic, rocky nucleus layered with regolith and venting frost. Quietly, several researchers said what many were thinking. The object had entered a new phase, a new state, a state where the tail was no longer needed, where outgassing had gone still, where the remaining structure seemed optimized for visibility, not decay. Could the tail have been a shield, a temporary outer skin now discarded? Could the brightness surge be what happens when that layer falls away and something more efficient is revealed beneath? There's no proof, but the timing remained impossible to ignore. The anti-tail vanished. The polarization stabilized. The brightness surged, and then nothing changed. No drop, no fade, just a calm, constant shine. 3I Atlas was no longer behaving like a fading comet. It felt almost like an object that had finished transforming, and now simply held its light, patient and ready. And while ground-based observers watched that strange stability, monitors near the edge of the heliosphere detected something else. A magnetic curl forming, not near the comet, but in the outer heliopause itself. The heliopause is the boundary where the sun's wind slows and yields to interstellar space, far beyond the planets, near the limits of our solar bubble. Normally, changes out there are slow, gentle gradients, ripples from storms that take months to arrive. But on the morning of December 11th, the pattern shifted. Voyager, transmitting from deep interstellar space, detected a sudden curling distortion in the magnetic field just beyond the heliopause. Meanwhile, NASA's Interstellar Boundary Explorer, IBEX, and data from the newer IMAP mission both logged a twist, an unexpected spiral compression forming in the magnetic sheath around our solar system. At first, It seemed unrelated to 3I Atlas. After all, the comet was nowhere near the heliopause. It was still in the inner system. But the timestamps told a different story. The curl began forming at the exact moment the anti-tail collapsed and the Doppler profiles vanished. Not before, not after, during. The synchrony was too tight to dismiss. Magnetic curls in space aren't random. They often arise when fields meet opposing pressures, like a vortex, but made of magnetism instead of water. For a curl to form at the heliopause, something had to apply subtle, coherent pressure to the heliosphere's outer shape, which raised the question, could an inner system object disturb the skin of the solar bubble? Under standard physics, the answer is no. The sun dominates that zone. Comets are small players, even interstellar ones. But this wasn't behaving like a typical comet. And what IBEX and IMAP observed wasn't turbulence, it was structure. A clean, clockwise spiral appeared in energetic neutral atom flux measurements. Normally, those atoms scatter outward evenly from solar wind collisions, but now they seemed redirected inward along an invisible curve. As if guided, it was as though the heliopause had grown a coil, a spring-like shape forming and holding. Some theorists connected it to a fringe concept called field resonance entanglement, the idea that large moving plasma sheets can trigger harmonics across vast charged particle flows, coupling distant regions. The theory remains on the edge of consensus, but it's gaining attention among researchers studying cosmic filaments and fast interstellar anomalies. If something like that occurred here, it would mean 3I Atlas somehow synchronized magnetically and directionally with the heliopause. No known natural mechanism explains such coupling, yet the coincidence in time, shape, and coherence suggested influence, not direct control, but resonance, a kind of magnetic handshake whispered across the solar system. For anyone simply looking up, nothing changed. The sky stayed quiet. The object still glowed, drifting toward Earth's orbit with steady calm. But at the edge of the solar system, where wind meets void, the heliopause curled inward, as if gently tugged, and in that moment, the only thing that had changed inside the system was 3I Atlas. By late morning, researchers moved into what should have been routine analysis. Residual thermal radiation from the ejected tail segment. When a comet loses part of its tail especially violently, there should be leftover heat across the region it occupied. Dust, gas, ice. They retain solar warmth, even in vacuum. Particles radiate infrared for hours, sometimes days. But 3I Atlas refused the familiar rules again. Across multiple observatories, IRTF in Hawaii, Sophia, and even James Webb, the expected thermal signature of the missing tail wasn't there. Not faint, not smeared, gone. Infrared imaging is one of the most reliable ways to find leftover mass in space. Even cold particles glow faintly in the right bands. A broken-off tail should leave a thermal footprint against the background, especially if it's dust-rich. Dust absorbs sunlight and re-emits it as thermal radiation. But every sweep between 0730 and 1000 UTC showed the same thing. A black void where the tail had been. No warmth, no emission, not even a whisper above the cosmic background. The data was so clean, it looked like the tail had never existed at all. That kind of thermal silence raised immediate questions. If the tail detached, where did the mass go? And how did it cool instantly? Some suggested rapid dispersion into an ultrafine cloud, too faint to detect. But scrutiny broke that explanation. A dispersed cloud still carries enormous surface area. It should create a diffuse thermal field. Yet the readings remained empty, as though the tail hadn't been matter. Others floated the idea of non-standard material, something that doesn't respond to solar radiation like ordinary dust or ice. But even silicates and carbon-rich particles radiate some heat. Then a darker possibility surfaced, quietly, cautiously. What if the tail wasn't lost or dispersed? What if it was reclaimed, radical, but disturbingly consistent with the data. If 3I Atlas had a way, natural or otherwise, to absorb, recapture, or neutralize its own outflow, that would explain both the disappearance and the lack of thermal residue. No particles left to heat, no surface area to glow, no trace to follow. A speculative framework entered discussion: cryogenic folding, a theoretical process where ejected material is compacted and cooled rapidly through internal sinks or radiation manipulation. The concept exists in advanced spacecraft shielding models, but not for natural bodies. Still, it fit the timing with eerie elegance. The anti-tail collapsed, the Doppler signals vanished, and afterward, the infrared ghost everyone expected never appeared. The instruments were ready to receive an afterimage. What they received was silence. The unsettling part wasn't only the missing heat, it was the sequence, the way it felt arranged, as if the tail had served a function, then ceased on command, not blown off, dismissed, and in its place, no radiation, no dust, no warmth, only the cold, hard stillness of interplanetary space, clean, unmarked, emptied. As the day continued and observatories stabilized, researchers noticed another disturbance, not as violent as the fracture, not as eerie as the thermal void, but potentially more significant. The jet vectors of 3I Atlas, the directional emissions from its nucleus, began to reorient, but not outward. As expected, they were shifting toward the sun. At first it looked like an error. Comet jets form when sunlight heats exposed volatiles, gas escapes outward, and pressure plus solar wind push material away or sideways depending on spin. A simple equation: sunlight hits, ice sublimates, gas vents outward. Comet dynamics 101. But spectral data and high-resolution imagery said otherwise. What had been messy, multi-directional jets, now narrowed into streamlined, sunward-facing lines. As if the object had turned its thrusters around, 3 independent confirmations followed. The Very Large Telescope in Chile saw a vector shift in polarized imaging at sunrise. Lick Observatory verified it with spectroscopic velocity mapping, and SOHO registered a faint forward emission within its coronagraph view, particles accelerating toward the solar center line. The contradiction was profound, and worse, it echoed what had already happened. During the anti-tail event, material had moved sunward briefly, and many hoped it was a one-time geometry oddity. Now the forward vectoring looked persistent. Not one jet, several, and they appeared coordinated. If sublimation were driving it, we'd expect randomness, chaotic bursts where ice happened to be exposed. But this alignment looked geometric, linear, symmetrical. The jets reoriented as if following an internal axis. That suggested either a complete restructuring of internal heat flow, rerouting venting through specific pathways, or an artificial process governing where, when, and how thrust was produced. Some researchers discussed rotational vector stabilization, a deep space maneuver where controlled mass ejection adjusts orientation. In spacecraft, it's done with mapped nozzles. In comets, it isn't supposed to happen, yet here was 3I Atlas pushing material toward the very star that should be pushing it away. The implication was quiet, but enormous. If an object can push sunward using internal forces, it isn't merely following passive orbital mechanics. It's adjusting, realigning, responding, or aiming. That possibility stirred intense, hushed debate among specialists in orbital dynamics and astrophysical fluid mechanics. Could 3I Atlas be using sublimation as controlled thrust? Could the sun be more than a heat source, maybe even a destination? Whatever the motive, one conclusion surfaced with unsettling clarity. 3I Atlas wasn't simply venting anymore. It was steering. And after the jet reorientation, attention turned to the object's light signature, its spectral fingerprint. Every object in space reflects or emits light in patterns we can break down. Composition, texture, temperature, behavior. Comets usually show complex spectral lines, peaks and valleys from carbon compounds, hydrogen, sodium, water vapor, dust. But on December 11th, a different pattern began to unfold. As telescopes tightened focus, the spectrum of 3I Atlas started flattening. Those sharp lines began to fade, not gradually, but smoothing into a featureless curve. At first, teams suspected calibration error, solar interference, atmospheric distortion, a tracking mislock, but the pattern repeated across multiple observatories and spacecraft, independent systems confirming the same quiet truth. It wasn't the instruments, it was the object. Over 2 hours, the once intricate signature began to resemble a blackbody curve. Smooth, idealized thermal emission with almost no fine structure. That kind of curve is common in stars or in heated metals under controlled conditions, not in fragmented cometary bodies drifting in from another star system. More unsettling was the timing. The flattening began just after the jets reoriented. Brightness stayed steady, but the color profile shifted subtly toward infrared, while traces of earlier materials, carbon monoxide, silicate dust, seemed to vanish from the readout. No emission spikes, no absorption gaps, just one smooth arc. Quiet, clean, and wrong in a way that felt deliberate. What does it mean when a comet begins behaving like a perfect radiator? It suggests the light isn't coming from chaotic surface reactions anymore. It suggests uniformity, or something that only looks like a surface. A shell, a smooth structure, a regulated field controlling how light escapes. Scientists debated whether the tail loss had revealed a fundamentally different core, or whether the body's exterior had rapidly reconfigured, melting, folding, restructuring into a new state. Veteran astrophysicists noted spectral flattening like this has never been observed in comets. Not in Oumuamua, not in Borisov, not in Hale-Bopp, Anchor, or Hyakutake. It doesn't belong to any known comet life cycle. In fact, it runs opposite to expectation. As comets break down, spectra usually become noisier, more chaotic, not smoother, not calmer. In a natural comet, the story usually gets messier. It fragments, it breaks down, it exposes new layers and releases stranger, heavier chemistry from within. But 3I Atlas wasn't growing more complex. It was becoming simpler, cleaner, sterile, controlled, as if it was shedding not only material, but its identity as a natural object, and the light it gave off featureless. Calm no longer carried the signature of chaos. It carried the signature of intention, and as the spectral profile kept flattening, stripping away every hint of volatile life, a new visual anomaly appeared. A faint ring barely there at first, then slowly sharpening with each pass of careful enhancement. The detection came from ESA's solar orbiter, watching from a vantage closer to the ecliptic plane than most earthbound scopes could manage. At approximately 1120 UTC on December 11th, the orbiter captured a sequence of high-contrast frames, a perfectly circular feature, forming just ahead of the main body of 3I Atlas. Not a flare, not a tail fragment, a thin, radiant ring dim, but consistent, encircling the object with geometric precision, like a drawn line that refused to tremble. At first it was dismissed as lens reflection, a solar artifact, the kind of phantom shape instruments sometimes invent. But the ring persisted across angles and filter settings. Infrared showed no heat signature. Ultraviolet revealed a mild fluorescent outline, like particles being gently excited by sunlight. It wasn't glowing from within. It was reacting, and the reaction made an outline too smooth to feel accidental. Stranger still, the ring wasn't stationary. It seemed locked to the object's rotation, keeping a fixed radius and a steady tilt while turning slowly, as if tethered by magnetic or gravitational constraint. Natural halos and coma expansions blur and wobble. This didn't. Even the spacing from the core held steady from one observation window to the next. The ESA team cross-checked with other platforms. Gaia registered subtle deviations in local particle statistics. Bepi Colombo noted a small anomaly in flow consistent with a boundary, something shaped, not simply gaseous. The data hinted at electrostatic repulsion, plasma confinement, a kind of invisible fence that, under the right illumination, could become visible as a ring. Theories rose quickly, like whispers in a dark control room. Some compared it to shepherd moon dynamics, how small bodies maintain ring structure in Saturn's system through delicate gravitational nudges. Others suggested centrifugal trapping material spun off, then stabilized by momentum and field effects. But the truth was, it didn't behave like any natural ring system we'd catalogued. There was no debris field, no clumping, no slow outward drift. The particles, if particles were even the right word, stayed in perfect alignment, not colliding, not dispersing. No visible mass exchange bridged the ring and the main body, and in some contrast profiles, it almost looked as though the ring might not be matter at all, but a distortion in light itself. A few radical voices inside ESA murmured about frame lensing, a hypothetical phenomenon where localized curvature or field geometry bends incoming light into a ring-like signature. It wasn't mainstream, but it wasn't pure fantasy either. Einstein rings exist, but those belong to galaxies and gravity on cosmic scales. This was closer, sharper, almost managed. If 3I Atlas was bending light around itself, then it wasn't just a comet anymore. The more conservative explanations tried to hold the line. Maybe it was dust. Maybe it was a temporary belt created during the tail ejection. But the problem remained. The shape was too perfect, too cold, too quiet, and as the hours passed, it didn't fade. It became more defined. It seemed to harmonize with the spectral flattening. It rotated in step with the new jet alignment. And to anyone watching carefully, it suggested 3I Atlas had entered a phase not of decay, but of construction. Whatever had torn away the tail had cleared the stage for something else to form. And now that something was circling it flawless, still, faintly luminous in the sun's gentle pressure of light. By late afternoon on December 11th, Hubble was cleared for a fresh sequence of high-resolution exposures, aimed directly at the central mass of 3I Atlas. With the ring's appearance and the flattening spectrum already unsettling the quiet corners of the field, there was one goal: resolve the nucleus, pin it down, see what was left at the heart of this object. But what Hubble returned wasn't what anyone expected. Instead of a bright, icy core, what most assumed would remain after tail loss, Hubble caught a shadow, not cast onto space, but embedded within the object itself. In the raw data, it appeared as a small, ultra-dark central void, a region of dramatically reduced reflectivity that refused normal exposure compensation. Adjust contrast, layer filters, change bands. The center still wouldn't resolve. The perimeter showed faint gradients, scattered light along the edges where jets had once been tracked. But the middle offered nothing. A black disk, cold, opaque, unmoving, not a silhouette from an external light angle, not a shadow thrown across dust, a non-reflective zone inside the body like light entered and simply did not return. At first, STSCI analysts suspected an instrument artifact, a reflection flaw inside the imaging array, but alternate wavelengths confirmed the same geometry: near-infrared, ultraviolet, polarized light. All showed the same unwavering central void. Some called it a cavity, others an absorption zone. A few cautious voices used a softer word, a blind spot borrowed from optics, not astronomy. But the implications sharpened quickly. If the core wasn't scattering or emitting in any wavelength, then something fundamental had changed. Even a comet's nucleus behind dust and gas reflects something: surface granularity, mineral content, residual activity. But this was perfect darkness. And unlike a black hole or a neutron star, 3I Atlas didn't have the mass to trap light by gravity alone. It wasn't heavy enough. It wasn't massive. So what was suppressing the photons theories arrived within hours. One proposed a collapsed interior densified, non-reflective material, perhaps a carbon-rich shell cooled and hardened after the tail event, blocking outgoing light. But thermal maps didn't support it. There was no infrared heat suggesting compaction or stress. Another theory leaned into field distortion, electrical or magnetic structures interfering with incoming and outgoing photons, creating localized invisibility. It's simulated in plasma labs, but never seen in nature at this scale. Then came the chillier possibility that this wasn't a shadow at all, but a deliberate cloaking field, an optical silence designed to hide the interior, something at the center of 3I Atlas. The silence around that idea was its own kind of evidence. It wasn't mocked. It wasn't dismissed. It simply vanished from official summaries. Public briefings called it anomalously non-reflective, requiring more study, but off record, among tight circles of deep space physicists and spectral imaging teams, the phrase stuck, core shadow, because that's what it looked like. A flat, round, unwavering patch of darkness, where light refused to linger. And if that shadow wasn't a side effect, it might have been the objective. As the chaos of tail separation settled into a strange quiet, attention turned to what the object had left behind. After the detachment, observatories expected the debris to behave like any natural ejection spreading into solar orbit, breaking apart, interacting with radiation and wind in predictable ways. But instead of a noisy aftermath, a pattern emerged that felt like a mission. There was nothing. No detectable radio reflection from the tail debris. Normally, fragments and outgassed material scatter radio waves, especially at longer wavelengths used for deep space radar and Doppler mapping. Even small icy grains can return faint pings when scanned by high-gain arrays' successor radar platforms and the Deep Space Network. But when those systems focused on the trail of ejected mass drifting behind 3I Atlas in a curved spiral, what came back was a void. No bounce, no echo, no distortion, no phase delay, as if the particles had become invisible to radio. At first, teams blamed interference. December 11th had solar noise in certain bands, but after rerouting through cleaner windows and coordinating pings across Europe, South America, and the Lunar Pathfinder Array, the result held. Radio silence. Not atmospheric, not accidental, a deliberate absence, which raised the urgent question, where did the debris go optically? Powerful scopes still saw a diffuse cloud spreading in a shallow arc. It shimmered faintly, like dust, but it didn't reflect light the way water, ice, or silicate grains normally would, and more disturbingly, it refused electromagnetic interaction. No radar signature, no microwave scatter, no L-band or X-band return. It absorbed incoming signal as if coated or fundamentally changed. A group of atmospheric physicists noted the resemblance to stealth materials in aerospace design, engineered to absorb waves or scatter them away from the source. That kind of material requires microscopic structure, complex patterning, yet here it was, implied in a drifting cloud of comet fragments in open space. Then a second anomaly surfaced. The debris wasn't decelerating the way a natural cloud should. After an ejection, fragments usually spread, slow, and begin obeying solar pressure and gravity in familiar ways. But this arc held formation unnaturally well. Its curve stayed coherent, as if mildly tethered, or guided along field lines. It didn't drift like dust. It hovered, and it answered nothing. The behavior defied decades of comet tail dynamics. It was more than silent. It was ghost-like present to optics, absent to the electromagnetic spectrum. A few researchers suggested we might not be looking at debris at all, but something else, a shell, a veil, perhaps even a decoy, What if the ejection wasn't rupture, but design? What if the tail wasn't lost, but shed on purpose thermal shielding, visual camouflage, mass balancing? A layer that had completed its assignment, and now what remained behind was engineered not to respond, not to reflect, not to reveal. A quiet field drifting behind a shadowed core, and in that hush, radio telescopes found their first undeniable hint of intent. Because in space, noise is common, silence is built. As the fragments drifted behind it, observatories turned back to the object itself, searching for continuing activity. Most comets remain active long after tail disturbances, volatile ices still sublimating as sunlight penetrates deeper layers. But with 3I Atlas, something stranger happened. Outgassing fell to zero, not slowly, not with a gentle decline. It stopped sudden and complete within hours of the separation. The first warning came from the sub-millimeter array in Hawaii, tracking molecular lines: carbon monoxide, cyanide, formaldehyde, the usual fingerprints of internal activity. They expected at least a faint echo. Instead, the instruments found nothing. ALMA confirmed it in Chile. IRAM confirmed it in Spain. Across every radio band where signatures should have lived, the lines were flat. No ammonia, no methanol, no water vapor, not even the thin whiff of dust ions that often lingers as an object stabilizes. The outgassing had gone dark, unprecedented for something this close to the sun. Even inert asteroids can show slight degassing under sustained solar heating, trapped material bleeding out through microfractures. But 3I Atlas, after shedding its tail, seemed sealed. Some argued for rapid crust formation, a newly exposed layer that cooled into a thick shell, locking activity behind it. Yet thermal readings didn't support that story. The surface remained warm enough that sublimation should have continued. If anything volatile remained, so a more radical possibility surfaced, that the material beneath wasn't volatile at all. Either it had been exhausted, or it had never been natural to begin with. What emerged now was not a dormant rock, but something deliberately inert, an object that had transitioned from dynamic emitter to quiet body, oddly immune to the sun's persuasion. The optical behavior made it stranger. Without coma and gas, it should have dimmed, but it held steady, no fade, no haze, no distortion, as if the coma hadn't dissipated, but retracted. Spectropolarimetric readings from SOFIA reinforced it. The light scatter halo collapsed. The surrounding fog was gone. The body remained sealed, reflective, but no longer reactive. A few researchers suggested we might be watching the final phase of an artificial shedding process, a purge of unnecessary outer mass, followed by structural lockdown. If this were a vessel, a probe, even a decoy, this would be the moment it revealed the form beneath the disguise. A core that doesn't emit, a body that doesn't vent, a casing that no longer breathes. And, in private notes, the word comet began to fade away. Because comets don't simply stop outgassing, they weaken, they fracture, they sputter. 3I Atlas did none of that. It closed, it shut off, it chose silence, and in that stillness, it felt like it was preparing for whatever came next. By the evening of December 11th, a quiet shift rippled through multiple NASA centers, analysts combing data from the Deep Space Network. Hubble and JWST stopped framing 3I Atlas as a typical cometary event. Behind closed doors, terminology changed. Not ruptured, not broken, not even fractured, disengaged. The word appeared in a secure thread between Goddard and JPL, summarizing the tail loss incident near Mars's orbital path. The conclusion calm. Clinical felt unnerving in its certainty. It didn't fragment. It disengaged. Not failure. Sequence. The tail, dense and ion bright only hours earlier, had separated cleanly, more like controlled detachment than stress rupture. The velocity gradient across the departing mass was uniform. The separation angle was symmetrical. No tumble, no thermal irregularity, no stress signature on the main body. To an aerospace eye, it didn't read as a break. It read as procedure. Engineers with deployment system experience were brought in, people used to modeling staged releases and mechanical separations. Their assessment was blunt. The departing material behaved like a stage release, like shedding an external tank or dropping a protective shell. Once that comparison landed, the questions multiplied. Why would a comet execute a release maneuver? Why would it be balanced, clean, timed? And what exactly was left behind? Because what remained didn't look injured. It held course. It produced symmetrical jet vectors. It operated without the signatures of natural comet behavior. Volatile layers gone. Outgassing ended. Core masked. And in the absence of debris chaos, it looked, disturbingly, operational. That phrase didn't appear in public briefings, but it surfaced in a preliminary internal summary forwarded to the Office of Planetary Defense. Under trajectory integrity, the object was described as retaining flight stabilization post-disengagement. In plain language, it was still flying like it was meant to, unlike fragmented comets, which wobble and drift after major mass loss. 3I Atlas stayed locked on its vector. No meaningful angular change. No drift. It detached and continued lighter, quieter, somehow more precise. And the absence of chaos was the most disconcerting part. Natural breakups create unpredictable signatures, rogue particles, delayed outbursts, messy spins. This didn't. Analysts stopped forcing comet templates onto the data. They began reaching for mechanical analogies, jettison protocols, capsule releases, modular staging events, and quietly, in rooms without microphones, some said what no one would ever type into a press release. This wasn't a breakup. It was a systems command. It didn't explode. It didn't crack. It let go. And now, with half its mass behind it and a sealed core ahead, 3I Atlas wasn't behaving like something reacting to sunlight. It behaved like something that had completed a phase and stepped into the next. Just as the scientific community began adjusting to disengaged, the sun responded not with a familiar flare or a standard coronal mass ejection, but with something stranger. Precisely 14 hours after the tail detachment, solar observatories recorded a spiral-shaped jet erupting from the sun's equatorial region. Unlike violent, chaotic ejections, this event unfolded with eerie symmetry. It didn't fan out. It didn't splinter. It unfurled in a spiral, as if unwinding from a central point. Thin bands of plasma twined outward like a coil, holding geometric integrity as they pushed into the heliosphere. First spotted by SDO, the jet appeared as a glowing helix, twisting out of the photosphere and reaching into space like a corkscrew. Solar jets are usually linear or fan-shaped products of sudden reconnection. A spiral implies rotation, a spinning origin fast enough to braid escaping plasma into a filament. SOHO confirmed it, and confirmed something else. It didn't dissipate quickly. It held form for millions of kilometers, subtly rotating as it traveled, visible across bands from ultraviolet to X-ray. At no point did it fragment or veer. It behaved like a thread pulled tight, stretching between the sun and something beyond the usual narrative. That something was 3I Atlas. Its position on the trailing edge of Mars's orbit placed it loosely downstream from the jet's trajectory. Not a perfect line, but close enough to raise careful alarm. Was the spiral jet a coincidence? A rare flux rope formation finally captured with exceptional clarity? Some argued yes. Others couldn't ignore the timing or the shape. Stereo A offered a key clue. Magnetic field models of the jet's path showed convergence rather than diffusion. Instead of spreading, the vectors stayed tight, guided, coherent, even after traveling millions of kilometers. One analyst described it as a guided stream of solar breath, and 3i Atlas showed no obvious reaction. No thermal bloom, no deviation, no dust shroud. If anything reached it, it passed like wind around stone. And that raised a darker question. What if the spiral jet wasn't meant to strike the object, but to reach it? A connection attempt. A signal. Because comets react melting, flaring, shedding. This one had gone quiet, and then watched. And the sun, in an act unlike its well-documented habits, released something not explosive, but elegant, structured, directed, and for the first time, it wasn't clear which one initiated contact, the comet or the star. As the spiral jet slowly loosened into space, instruments recalibrated, and attention returned to 3i Atlas. But what came next deepened the mystery. The object silent, sealed, no longer outgassing, was not dimming. It was brightening. By every comet model, it should have faded. No tail, no coma, no cloud of reflective grains. Solar energy input had dropped below the threshold needed to sustain luminosity. And yet, IVST, pan-stars, and even careful amateur logs showed a steady uptick in reflected brightness. The numbers didn't settle. They climbed. Inside NASA, a phrase resurfaced in internal briefings: energy budget violation. It wasn't new. Months earlier, near Jupiter, 3i Atlas had hinted at internal thermal retention inconsistent with a natural body. Those anomalies had been brushed aside, shielding effects. Albedo errors, the usual comforts. But now, with the tail gone and the coma vanished, there was nowhere for the discrepancy to hide. The math was simple. Incoming solar radiation could not account for the visible energy being returned. The object was, once again, shining more than it should, sustained not a flash, not a brief spike. The brightness held for hours. Theories tried to keep pace. Latent heat release, hidden pressurized pockets. But there were no thermal signatures, no emission spectra, no evidence of cracking vents. Another explanation leaned toward optical manipulation, a surface geometry or coating capable of amplifying reflected light in narrow bands. Not common in nature, but familiar in engineered systems. Stealth, illumination control, adaptive materials. Still, speculation couldn't soften the central fact. 3i Atlas was returning more light than it should be able to absorb or reflect. That meant energy was coming from somewhere else. Multiple labs ran recalculations, photon pressure differentials, scattering efficiencies, lensing variables. None could close the gap without introducing a second energy source, internal or external, which opened a question too heavy to say quickly. Was it powering itself? The math was simple, and it was unforgiving. The sunlight striking the surface wasn't enough to explain the visible energy coming back. Once again, the object was glowing more than it should. We've seen hints of this before. Brief, unexplained flashes from near-Earth objects, quick bursts during meteoric entries, but never like this. Not sustained, not so steady, not so controlled. The brightness held for more than 4 hours. One theory suggested latent heat release, slow bleeding from pressurized pockets inside. But there were no thermal signatures, no emission lines, no acoustic hints of cracks, vents, or stress. Another explanation turned to optical manipulation, a coating or geometry that could amplify reflected light in narrow bands, like a tuned surface catching only what it wants. That would imply an advanced structure designed to manage visibility across wavelengths, not something nature typically builds, but something engineers dream about in stealth and illumination tech. And through all the speculation, one fact stayed heavy in every report. 3i Atlas was returning more light than it should be able to absorb or reflect, which meant the energy was coming from somewhere else. Several labs, including a group at MIT's Haystack Observatory, reran the numbers with photon pressure differentials and gravitational lensing variables. No combination closed the gap without introducing a second energy source, internal or external, which led to the quiet question nobody wanted to say too loudly. Was it powering itself? And this wasn't a question of propulsion. 3I Atlas's trajectory remained clean, steady, unaccelerated. This was a question of intentional illumination. Why glow now? Why remain visible after the tail? The coma, and all that noisy, comet-like clutter had been stripped away. In one classified NASA document, an analyst offered a soft possibility. If the object had entered a phase of passive observation, the luminosity could be signal or calibration, a light meant to be seen, a beacon with a measured brightness. The phrase energy budget violation stopped feeling like a math error. It became a marker, a signature of something operating on principles that weren't natural to our models, not breaking physics, but following a logic our physics couldn't yet describe. Because this wasn't an explosion, not a flare, not a thermal spike. It was a controlled rise in visual magnitude, smooth, consistent, unforced, and when it approached its brightest point, it didn't crash or fade. It stopped, like a switch, quietly toggled. Stable again, silent again, no more light than expected, but no less than needed to remind us it was still there, and it knew exactly what it was doing. For weeks, the inner core of 3I Atlas had been hidden, first behind a dense coma, then behind restless tail structures, and finally behind the object's own deliberate quiet. But now, with the tail gone, outgassing halted, and brightness calm, astronomers finally had a clear, uninterrupted view, and what they saw wasn't what they expected. The core wasn't round. Data from the James Webb Space Telescope, backed by high-resolution stacked imaging from Earth, revealed something no comet had ever shown so clearly. The nucleus appeared elongated, not spherical. At first, some dismissed it as angle, shadow, or processing bias. But as more frames arrived across bands, and as the object rotated slowly through its solar geometry, the outline stayed consistent. It wasn't lumpy, it wasn't chaotic, it was precisely shaped, narrow and stretched, with clean, linear edges and a tapered end that looked almost finished. Some called it spindle-like, others said flattened cylinder, but no one could ignore the symmetry. Natural comet nuclei are rough and uneven. Even Oumuamua, with its startling cigar-like form, never presented surfaces this consistent. 3I Atlas was different. Its elongation was too centered, too balanced, too deliberate to wave away. Infrared readings showed a remarkably even thermal distribution along the entire length. No hotspots, no vents, no craters or scars of erosion. The surface looked smooth, unbroken, and most notably, it did not tumble with the clumsy chaos of a rock. It seemed to glide, holding a slow, stable axial alignment, as if guided by a quiet hand you couldn't see. Even more intriguing was the reflectivity differential across that surface. The tapered ends reflected slightly less than the central region, like a subtle design choice for directional masking. One analyst called it a visibility gradient, a property rarely, if ever, found in naturally formed bodies, and once you noticed it, you couldn't unsee it. Yet the shape alone wasn't what truly unsettled researchers. It was what the shape implied. Elongated cores aren't efficient for natural stability. They precess, they tumble, they fracture, unless something is stabilizing them on purpose. And behind the scenes, theories began to gather like low cloud. Could the core be a housing, a protective casing around something inside? Could that elongation serve function, shielding, signal direction, selective energy absorption? The question wasn't only what it looked like, it was why it looked that way now. At this exact moment in its journey, right after shedding so much of itself, the object had discarded its tail, it had silenced its emissions. It had entered what looked like a dormant cruise state, and now, fully exposed, it revealed a form that didn't fit any known comet classification. NASA analysts flagged the development as highly atypical. ESA's Near-Earth Object Coordination Center issued a cautious bulletin, calling it merely an uncommonly shaped nucleus. But off-record, in briefings with lowered voices, a new term started to circulate. Structure positive. In mission language, it meant the object showed more indicators of intentional design than natural formation. Not proof, but signal. Quiet. Cold. Waiting. Because what remained behind wasn't a dying rock. It was a core. Stretched. Symmetrical. Steady. And for the first time since 3I Atlas appeared, it no longer resembled a comet at all. It looked like a vehicle, one that had shed everything unnecessary, and now drifted in full exposure. Its geometry speaking in a language older than our labels. With the elongated core exposed and brightness plateauing across optical bands, analysts focused on a measurement that should have been routine: albedo. Surface reflectivity, a mundane confirmation step. Instead, it became the final crack in the natural theory as readings poured in from JWST, PAN-STARRS, and multiple ground-based infrared stations. A pattern emerged. 3I Atlas was reflecting more light than any known comet. Far more. Calculations suggested over 90% of incoming sunlight was being reflected. That number wasn't just high. It was nearly impossible for a natural body out here. Fresh snow on Earth reflects roughly 80 to 85%. Enceladus reflects slightly more. Even polished metals in controlled labs rarely exceed 90% across a full spectrum. But this was different. And it wasn't perfectly uniform. Reflectivity varied subtly by band, favoring specific wavelengths. In visible light, it peaked. In infrared, it dropped sharply, as if tuned to be seen only under certain conditions. In other words, it wanted to be seen, but only just enough. That kind of reflectivity suggests an engineered surface. Polished, smoothed, possibly treated to manipulate visibility. There were no signs of dust, debris, or natural frost layering. This wasn't chaotic ice. It looked like a pristine, light-controlling skin. A senior ESA optics engineer put it bluntly. If this was built, it was built to manage energy, not merely endure it. Because reflectivity isn't only about brightness. Surfaces that reject light also reject heat. With over 90% of solar energy deflected, 3I Atlas was absorbing almost nothing. In space terms, it was behaving like a mirror, a near-perfect one. And that mirrored quality carried another consequence. It masked thermal readings, with so little energy retained. Infrared telescopes had almost no signature to lock onto. From a thermal imaging perspective, the object became nearly invisible. Cold, featureless, quiet. Some theorized the jump in reflectivity wasn't evolution, but activation. A surface state that switched after tail detachment. Not a drifting body, but a body capable of changing itself on command. And with that mirror skin rejecting solar input, two interpretations began to circulate. Defensive mode, built to survive wind, UV, and scrutiny, or observational mode, reflecting precisely because it was now watching, collecting, waiting for contact. Either way, the natural comet hypothesis kept collapsing under its own weight. ESA quietly updated an internal status tag for 3I Atlas from comet-like to object of interest. JPL stopped issuing regular public updates, replacing them with irregular technical memos distributed only to high-clearance research circles and defense advisors. Because once a body controls how much light it reflects, and when, you're no longer studying a rock, you're watching a decision. Reflectivity above 90% isn't a feature. It isn't coincidence. It isn't accident. It's a choice. And somewhere inside that elongated core, behind that flawless mirror skin, something might still be watching us back. Untouched by heat, untouched by force, untouched by time. Visible only enough to tell us we were meant to see it. For months, astronomers had tracked 3I Atlas's chemistry across every observable band. Like most interstellar objects, its spectral profile carried familiar hints: trace carbon, oxygen, nitrogen, scattered, volatile organics, weak, but recognizable. Those faint signatures kept it within the realm of natural, even if barely. But in the early hours of December 11th, something changed. Carbon disappeared. Spectrographic scans from Mount Aya, ESO's Very Large Telescope, and JWST all confirmed the same quiet absence. The faint carbon absorption lines were gone. Not reduced, not drowned in noise. Gone. A clean ghosting event. Complete. Carbon is baseline in almost every body we've ever studied. Comets, asteroids, 2 moons, atmospheres. Carbon shows itself. Gas, dust, complex molecules, frozen solids. Even deep space comets carry it etched into their outer layers by eons. So when carbon vanishes from a known object without a trace, scientists don't shrug. They escalate. First suspicion was instrument error. Teams triple-checked timing, calibration, reference stars, correction models. But the result held. Carbon's tiny dips and peaks were absent across the core's reflectance path. And the strangest part, no other elements vanished with it. Hydroxyl traces remained. Sodium, oxygen, magnesium, all still measurable. But carbon, the backbone of organics, the staple of cometary dust, had been erased from the scan, and that opened the door to theories nobody wanted to step through. Had the carbon been removed? And if so, by what process? Removal implies activity, and activity implies choice. One working theory claimed carbon-rich outer layers flaked away after detachment, revealing a cleaner, more metallic interior. But that didn't explain the precision or the timing. Only hours after reflectivity crossed 90%, and after that spiral jet from the sun brushed close to its trajectory. Another proposal was colder. What if the carbon wasn't lost, but masked? Spectral masking exists as a concept in stealth technology. Suppress specific signatures, and you make key elements harder to detect. On Earth, we've barely begun playing with that kind of material science. In space, against the ruthless clarity of sunlight and instrumentation, you'd need something far more deliberate. Carbon isn't merely a chemical marker, it's a diagnostic tool. Its lines help measure age, temperature, composition. If 3I Atlas hid those lines through surface alteration or field manipulation, then it meant one thing: it no longer wanted to be read. A shutdown of organic markers, a rejection of classification, a transition into a quieter phase. And the lack of debris made it worse. No dust cloud, no new absorption in surrounding space, no trail of carbon moving elsewhere. It was as if the carbon hadn't departed, it had simply stopped interacting with light. Some clung to one last natural explanation. A rotational mask, one face turned away, another face revealed. Deeper, cleaner, perhaps metallic. But that again leaned toward design symmetry, and the elongated form had already challenged randomness. The truth grew harder to deny. Carbon was gone, and no one knew how or why. But if something chose to hide its building blocks, it knew it was being watched. And if it knew that, it may have answered by going dark in the one place we always look first. As 3I Atlas drifted beyond Mars's orbital track, and the silence of its missing tail deepened, attention shifted slowly towards something closer to the sun. Roughly 6 hours after the carbon lines vanished, a new anomaly appeared, a single bright spot, faint but unmistakable on the inner edge of the solar limb, just outside the corona. At first it was dismissed as artifact, The sun produces eruptions daily, but this wasn't a flare. It didn't expand. It didn't pulse. It didn't radiate outward. It simply sat there, clean, stable, intensely white, stationary, and detached from any obvious solar feature. Soho noticed it first in routine LASCO C3 coronagraph sweeps. Then SDO confirmed the same coordinate in extreme ultraviolet. Earth-based solar telescopes Big Bear and others reported matching signature in visible bands. Yet it fit no known solar behavior. Flares shift fast. Loops flicker. Prominences rise and fall. This did none of that. It held its intensity. And most confusingly, its location. It didn't drift with the sun's rotation. It hovered fixed against a background that should have moved beneath it. Within 20 minutes, two details rattled every team watching. First, the light was pure, an unnaturally clean spike across bands, visible, ultraviolet, near infrared, with no flicker, no decay. Second, it wasn't emitting heat, no coronal spike, no ionization shock. The region stayed calm, no burst, no disruption, light without fire. Then someone noticed the timing and the geometry. The bright spot sat on the opposite vector from where 3i Atlas drifted. Draw a line through the sun from the object's position, and the point landed almost on axis, an axis that had never mattered until now. What was it? A signal, a reaction, a marker, a reply? No one could say. Some suggested gravitational lensing of a background source, warped by solar mass, but no catalogued object matched that brilliance there, and lensing would smear into arcs. Not a single, punctual bead of white. Others whispered something more radical, that the light wasn't from behind the sun, but from within, or through it. That something precise had pierced the solar view in a way that didn't erupt, only appeared. Stable, silent, hidden where most eyes wouldn't look for long. One thread traced the vector back to 3i Atlas and suggested the object had sent something, or triggered something. Something we were never meant to catch unless we looked at exactly the right angle, at exactly the wrong moment. The bright spot lasted just over 6 minutes. Then it faded, no flare, no wake, no afterglow. The sun returned to normal as if nothing happened. But those 6 minutes changed everything, because when an interstellar object sheds its skin, silences its tail, hides its chemistry, and then draws a clean line through the sun, you stop watching only the object. You start watching the light, and you begin asking not what it is, but what it left behind. Hours after that bright spot vanished, JPL issued a quiet, game-changing update. It wasn't a headline. It was a correction, tucked into a routine orbital bulletin, a small adjustment to 3i Atlas's rotational data. But inside that correction was a revelation. 3i Atlas had changed its spin. Its angular velocity had shifted, not from collision, not from outgassing, not from any familiar comet mechanics. Angular velocity is usually among the most stable parameters in space. Set early, nudged slowly by gravity, impacts, or gradual venting. Even strong outgassing typically produces predictable torque, a slow wobble, a gentle drift. But 3i Atlas broke that rule. Data showed a rapid, asymmetrical adjustment in a window shorter than 30 minutes. Its rotational speed increased slightly, while its spin axis tilted away from Earth by a few measurable degrees. The shift was smooth, no chaotic tumble, no instability. It didn't spin out. It realigned quietly, precisely, for days. NASA teams tried to blame solar wind pressure, Jovian perturbations, residual torque from the detached tail. Nothing fit. Solar pressure was too weak at that distance. Jupiter's influence had passed weeks before, and with the tail gone and no new jets observed, there was no natural force left to twist it this way, which led to one troubling conclusion. The object had altered itself, like a spacecraft correcting its orientation without visible thrusters. Except there were no engines, no heat bloom, no momentum loss. just a deliberate change in attitude, as if it had decided where to face. And the timing was impossible to ignore. The shift came shortly after Carbon vanished, and near the same window as the bright solar point. 3 anomalies packed tight together. 3 turns of the lock, none explained by nature alone. The orientation shift carried another implication. 2. By changing its spin axis, 3I Atlas altered how it interacted with sunlight and how we observed it from Earth. Light curves skewed, reflectivity patterns shifted, thermal echoes became harder to pin down. It was as if the object had turned away not just from Earth, but from visibility itself. Some scientists called the angular velocity change a final act of concealment, a door closing softly behind it. Tail dropped, surface masked, spectrum cleaned, and now even its rotation refused to cooperate with our gaze. Others saw it as a pivot, a careful alignment towards something else, perhaps the sun, perhaps a point in space we hadn't thought to watch yet. Avi Loeb, when asked to comment, said only this: rotation is one of the few signals in the cosmos that tells us whether an object is free or guided. And with 3I Atlas, that freedom now seemed uncertain, because when a comet changes its spin on cue, with no visible cause, at the same moment light bends near the sun, it stops behaving like a comet and starts behaving like a craft, or at the very least, like something following internal rules we've never witnessed before. And now it was turning away, not tumbling, not broken, just repositioning, as if it already knew where it wanted to go next. The change was so small it nearly slipped past the eye. After the angular velocity shift, teams around the world kept updating 3I Atlas's orbit, expecting only minor variations from solar radiation pressure or gravitational flutter. But what they found next was something else entirely. The object's heliocentric course, its path around the sun, had adjusted, not drastically, but deliberately. For weeks, 3I Atlas had followed a clean arc, consistent with an inbound interstellar body shaped by solar gravity and its own momentum. Analysts had mapped the journey with precision, using deep space telescopes, Lagrange point monitors, and infrared satellites. Everything had fit. Until now. At roughly 8 hours after the tail detachment event and the disappearance of carbon lines, the trajectory began to drift from its predicted arc. Instead of continuing on its outbound slingshot path, it veered, just enough to raise every eyebrow at NASA's Goddard Center and ESA's orbital mechanics desk. A shift by a fraction of a degree, but across astronomical distances, it meant something enormous. It meant 3I Atlas was no longer simply coasting. It was adjusting. The alteration wasn't chaotic, and it didn't match an external shove from a flare or impact. It was smooth, curved, as if guided by an internal mechanism that knew exactly where to place itself within the architecture of the solar system. In response, orbital models had to be rewritten. Predictive simulations built on the original vector began to fail. Legacy comet tracking software was set aside, replaced by defense-grade physics engines, usually reserved for high-priority near-Earth tracking and avoidance. And once the new trajectory resolved, it told a chilling story. Instead of escaping the solar system as expected, 3I Atlas now aligned with a tighter elliptical path, pulling it into a longer solar orbit. It was no longer just a visitor, it was staying. What shocked many wasn't only the result, but the elegance of the maneuver. Comets that fracture or vent erratically tend to veer in messy ways, shedding debris, slipping into instability. But 3I Atlas maintained cohesion, no fragmentation, no plume, just a clean pivot, like a glider catching a silent thermal and correcting its course with perfect restraint. This wasn't what interstellar debris does. Astronomers compared notes, searching for any record of a comet self-adjusting into a closed solar orbit after perihelion. Nothing came close. The only precedents belonged to spacecraft. Some hypothesized the angular momentum change earlier, in Chapter 25, had been a prelude, a calibration, necessary before the orbital curve could be executed. In that sense, the spin and the path weren't separate mysteries at all. They were one sequence, a coordinated series of moves, and then it grew even more unnerving. The new trajectory positioned 3I Atlas to reapproach Earth's orbital plane, but from the opposite side of the Sun. Not on a collision track, but in a mirrored alignment, allowing it to run alongside Earth's orbit at a distant parallel. Some called it a shadow arc, an invisible twin path, far enough to remain unseen to the naked eye, but close enough to stay connected. Like a quiet companion in the dark. Why would any object do that? Stabilizing for observation, setting up a return, choosing a place from which to watch. Whatever the motive, it confirmed what scientists had been whispering for days. 3I Atlas was no longer behaving like an object on a blind trajectory. It was behaving like something with awareness of position, with orbital awareness. And the only things we've ever seen do that: carry guidance systems. This wasn't just a change in speed or spin. It was a decision, made in silence, but written clearly in the mathematics of its path. And now, 3I Atlas was not leaving. It was settling in. In the aftermath of the orbital shift, attention returned to the surface, or what remained visible of it. High-resolution imaging had always been difficult, tangled in an unpredictable light curve. But with the new orientation and stable arc, telescopes finally captured the clearest sequence of frames yet recorded. And what they showed was unexpected. The surface was changing, subtly, but visibly. Across 10 hours, a pattern emerged. The rough, jagged topography once marked by sharp albedo jumps. Irregular edges, broken protrusions began to soften. Craters, ridges, and chaotic markings that had defined its shell started to fade. Not from motion blur, not from sensor noise. Frame after frame confirmed across 4 independent platforms showed the same result. A uniform texture was forming, and it didn't make sense. Natural bodies don't become smoother over time unless exposed to erosion, tidal reshaping, or atmospheric entry. But 3I Atlas was in open space, far from planets, experiencing no friction, no wind, no pressure, no impacts, no thermal surges, no collisions. And yet the transformation continued, relentlessly subtle, undeniably real, one by one. The contrast between bright and dark zones began to neutralize. Regions that once flashed with sunlight dimmed, while dull zones began to catch more light. The result was a uniform grey-white sheen, like powdered metal or stone polished by patient hands. ESA researchers called it albedo convergence. NASA's imaging team labeled the set more bluntly, surface homogenization phase. The label didn't matter. The message did. The shell was becoming seamless, and it followed the earlier revelation that carbon signatures had vanished from the spectrum. With the tail already ejected and the trajectory altered, it felt as if 3I Atlas had entered a full-body transition, one that erased every identifiable surface marker. But why, one theory suggested self-healing material, like reactive polymers or nanoalloys on Earth, that sealed cracks under thermal or electrical stimulus. Another, more radical idea proposed: the surface wasn't smoothing at all. It was being covered. That's something fine, particulate mist, a reflective shell, even an electromagnetic layer, was wrapping around the object in slow waves, creating the appearance of smoothing while concealing what lay beneath. This gained traction when infrared readings began to show an unusual shift. Thermal flattening. Rough objects radiate heat irregularly. But 3I Atlas's surface temperature began equalizing across vectors, another sign that internal variation was being masked. If this was camouflage, it was working. Spectrometers began losing the ability to distinguish mineral types. Reflectivity tests stopped showing directional variance. Even radar returns came back with reduced scatter, as if the surface was absorbing and compressing signals into a narrow band. Simply put, we were losing the ability to see it. Avi Loeb was among the first to connect the dots. If this were a probe, he said quietly, this is what it would do before going silent. Because in the vacuum of space, visibility is vulnerability. And if 3i Atlas was preparing for something observation, redirection, activation, contact, it would first make itself invisible to noise. No flare, no flash, just a shell becoming smooth enough to disappear into light itself. And so the object that once danced with jets and carried a bright tail across the stars was now polishing itself into silence, or worse, preparing for the next move. Just as the surface became unnervingly uniform, another development unfolded, one that contradicted everything from the previous hours. The backscatter returned. For days, astronomers had noted a decline in reflective returns. The increasingly polished shell seemed to absorb or deflect meaningful bounce, making optical and radar tracking feel dull, nearly useless. Instruments designed to measure reflectivity across wavelengths registered almost flat responses, as if the object were deliberately cloaking itself. Then, without precursor, that silence broke. A spike in backscattered light, sharp, clean, coherent, flashed across ESA's optical ground stations, followed moments later by near-identical returns from NASA's infrared and microwave observatories. At first it looked like error. Calibration was rerun. Models were checked. The result held. Light that had once vanished on contact was now bouncing back, and not randomly. It was directional. Unlike natural bodies that scatter unevenly with composition, rotation, and incidence angle, 3i Atlas returned light in consistent arcs, centered around 2 points near its equatorial plane. The symmetry was geometric, unmistakable. It wasn't merely reflecting, it was behaving like a signal. Some called it a bloom, others named it surface resonance, but the return patterns were too clean, too deliberate. It looked like a calculated refractive response, as if concealment had ended and visibility had been chosen, which opened a deeper question. If it chose to reveal itself again, why now? And what had changed? Some theories focused on its new orbit. By settling into that mirrored trajectory opposite Earth, it may have been attempting an optical handshake, a light return designed to be seen from a specific angle by a specific observer. Others argued the smoothing wasn't only for hiding, but for preparing a reflective operation, a shell like a dish, a panel, a controlled mirror. Not diffuse reflection, but aimed. This gained weight when scientists reviewed early inbound data. Back then, 3i Atlas had flickered brief bright returns followed by sudden silence. Many blamed tumbling or jet interference, but in hindsight, it resembled a pattern, repeating now with sharper precision. And then another anomaly arrived. The returning light began to polarize. Standard solar reflection rarely shows strong polarization unless filtered through crystalline structures or engineered surfaces. Yet 3i Atlas's backscatter began aligning along single-axis polarization bands. It wasn't only returning light, it was filtering it. To optics experts, this was no longer a passive surface. It was an interface. Avi Loeb voiced what many were thinking, almost under his breath. When light returns like this, we're no longer just observing it. We may be being observed back. The implications were immediate. Satellites shifted tracking protocols, deep space arrays moved into full spectrum monitoring, and for the first time since the tail detached, the possibility of two-way observation took center stage. It wasn't a flare. It wasn't a solar accident. It felt like a controlled reply, quiet to most, undeniable to those watching closely. 3i Atlas had spent hours shedding its identity. Now it was sending something back. Not words, not code, just light, refined, structured, intentional, and somewhere in that cold geometry, it was watching us watch it. It didn't arrive with sirens or headlines. It arrived as a quiet bulletin, slipped into the international feed just after 3 in the morning. The Minor Planets Center, the global clearinghouse for object tracking, issued an observation priority upgrade for 3i Atlas. To the public, it sounded procedural. To those who understood the language, it was unmistakable. Something had changed, and the world was being told to watch. The designation moved 3I Atlas from standard transient traffic comets, asteroids, interstellar passers-by, into a narrower category of active monitoring targets. Only a handful of bodies are flagged this way. Most are near-Earth objects with impact potential. Some are unclassified anomalies. A few like Oumuamua before it sit in that grey zone of unknown intent. But almost none receive a mid-orbit escalation like this. What triggered it wasn't only the backscatter returning, nor only the orbital shift. It was the combination. A climbing ladder of anomalies, painting the picture of something no longer inert, no longer random, and no longer easy to model. Within hours of the bulletin, observatories around the planet redirected telescope time. Deep field slots were overwritten. Planetary campaigns were paused. Even non-optical instruments, radio arrays, gamma sensors, LiDAR units were retasked. Why? Because the data was converging on a truth few wanted to speak plainly. 3I Atlas was behaving like an object under control. The center's internal notes, later leaked to independent researchers, outlined the reasoning behind the upgrade. Among the factors cited were the controlled smoothing of its surface, the return of polarized backscatter, the intentional angular shift in orbit, the loss of volatile material without fragmentation, and the synchronization with Earth's orbital plane on the far side of the Sun. And maybe the most chilling detail of all was the lack of natural decay. Cometary bodies usually unravel with time. Their skins fracture, their cores vent, their paths tremble as cohesion slips away. But 3 Atlas was doing the opposite, becoming more coherent, more stable, more deliberate. So when the Minor Planet Center issued an observation upgrade, it wasn't just asking astronomers to write cleaner notes. It was quietly signaling that something larger was unfolding, and the usual catalog language could no longer hold it. In response, a dozen private space companies, many under government contract, were ordered to submit every unpublished frame and trace. The object's profile was uploaded into defense-grade modeling systems, the kind typically reserved for national security, satellites, and launch windows. This wasn't about collision, it was about intention. 3 Atlas had crossed a threshold from foreign debris to a known actor, a presence. And the words inside official reports began to change. Anomalous light behavior became directed reflectivity. Orbital instability softened into course correction. And most telling of all, for the first time, several agencies began referring to it not as a comet or a rock, but as a body of interest. Not dangerous, not yet but important enough to bend the full weight of Earth's scientific apparatus toward it. This wasn't surveillance, it was acknowledgement. Something had arrived, something had changed, and now, with telescopes pivoting and models recalibrating, the world's scientists stopped guessing. They watched closely, quietly, because the object that once roared in with fire and mass was now drifting in plain view, rewriting the rules as it went. And in the early hours after the Minor Planet Center's upgrade, something subtle, unsettling, began to emerge from the radio data. It wasn't a flare, it wasn't a spike, it was a pattern buried in low-frequency telemetry from long-range arrays. Chile, Australia, West Virginia. Analysts began noticing a repeating pulse, not loud, enough to set off alarms, not shaped like a transmission, but present, persistent, returning every 48 minutes. It wasn't a new frequency, and it hadn't arrived with a dramatic burst. It had been sitting in the background for at least 2 days. Only now, with heightened protocols, were the timestamps and amplitude graphs clean enough to isolate it. Every cycle matched the last. A soft rise in signal strength, a sharp plateau lasting 4 seconds, then a clean decay, resetting the loop. It didn't match solar wind harmonics. It didn't align with known stellar pulse cycles. It wasn't an echo of Earth infrastructure. It was coming from the vicinity of 3 Atlas, and the band itself made the discovery feel stranger. It lived down in the very low end of the time domain, barely above the noise floor, where only a handful of natural processes produce regular signals. But this one was too clean, too consistent, too intentional. The first to raise an alarm was an independent researcher in New Zealand who posted an unlisted report on a familiar astronomy forum. Within hours, the post was flagged, locked, removed, but not before researchers in Europe and North America verified the data themselves. The consensus was cold. This wasn't random. This wasn't thermal noise. It was clocked, like something measuring time and speculation. Predictably, bloomed. Some suggested internal calibration, a feedback loop, like the quiet housekeeping cycles of satellites and spacecraft. Others wondered if it came from rotation, from oscillation within the object, but the data refused those comforts. There was no matching rotation signal, no magnetic variance, no mass shift that would hint at wobble or spin. The object wasn't rotating in a way that could explain a pulse every 48 minutes. Instead, it was emitting a signal tied to nothing but time itself. And the longer analysts stared at the return curves, the heavier the implications became. If it wasn't decay and it wasn't motion, then it was purpose. Maybe not a message, but a heartbeat, a baseline, a marker of uptime, perhaps a trigger. And at the exact midpoint of each 48-minute cycle, astronomers began to notice something else, a faint polarization in the returning light, too brief to measure conclusively, but present enough to make people ask in low voices, is this object syncing itself to something? And if it is, what is it? Syncing with JWST was briefly repositioned to capture reflected infrared at the peak cycle. Nothing anomalous appeared in the frames, but the timing, the regularity, silence. The precision placed 3 Atlas into a category. No scientist wanted to name an engineered rhythm, not an SOS, not a language, a cadence, steady, unchanging, ignoring the sun. The planets, the magnetic fields, as if it were simply counting time in the dark. 48 minutes, every time, no variance, no modulation, just a low whisper, pinned to the cosmos. And it was still going. Whatever 3 Atlas had become, it was. Awake. While most eyes stayed fixed on deep space behavior, something shifted closer to home, subtle at first, then impossible to ignore. At approximately 2:40 inches the morning, UTC, unexpected auroral activity flared over northern Canada, Scandinavia, and parts of eastern Russia. The event lasted just over 11 minutes, and what made it remarkable wasn't brightness or reach, it was timing. The aurora spike coincided perfectly with one of the 48-minute signal pulses. Ground observers, it looked like a thin band, green and red, intensifying fast, then fading like breath on cold glass. Too short for most commercial tours to catch, but satellites captured it in full detail. What puzzled experts wasn't only the brevity, it was the absence of a solar trigger. Auroras usually follow solar wind particles slamming into Earth's magnetic field, especially after coronal mass ejections. Yet that night, the sun was calm. No flares, no CMEs, no spikes in geomagnetic indices. Forecasts showed nothing unusual: solar wind, steady proton flux. Lo, there should have been no aurora at all. And yet it came, a flash from above, then gone. Stations began pulling logs, searching for the brief magnetic fluctuation that had preceded the light. The disturbance didn't fit solar interference. It arrived as a tight burst, a pinprick to the magnetosphere, then rapid dissipation. Source direction logged as outbound well beyond lunar orbit, and the trajectory lined up precisely with 3 Atlas's path behind the sun. For a few hours it was filed as coincidence. Then came the second auroral pulse. Roughly 48 minutes later, another brief arc of color in the same high-latitude regions, even shorter, barely 6 minutes. Still no solar activity, still no proton events, just a magnetic twitch, a quick surge in ionospheric activity, and then light dancing silently across the sky. Now, the evidence was harder to ignore. An object millions of miles away had produced a measurable effect on Earth's magnetic field. Twice, scientists at NOAA and ESA's space weather prediction teams issued internal queries. Was this a high-frequency energy pulse, a byproduct of gravitational resonance? The models said no. Earth's position wasn't aligned for any known magnetic interaction. No predicted resonance window, no current sheet crossing. The magnetosphere should have been still, and yet the lights danced again, leaving one unnerving theory. What if the object was probing, not attacking, not signaling, nudging just enough to test the envelope of Earth's magnetic shell, like sonar, like echolocation, like something learning the shape of what it had approached? There was no damage. Satellites remained online. Radio transmissions were unaffected. But the precision of the timing and the lack of any natural precursor set off silent alarms in defense and research circles alike. Backscatter polarization from 3 Atlas spiked in the same window, suggesting the object may have anticipated the aurora response or even caused it. And so for a few minutes the skies above Earth glowed without flare, without warning, without the sun. Something out there had reached in, not loudly, not obviously, just long enough to say, "I see you." Then, as suddenly as it began, the color vanished, leaving only quiet magnetic records puzzled scientists and a growing sense that Earth had been gently tapped from afar. It wasn't dramatic, no electromagnetic surge, no long auroral trail, and yet, among the world's orbital observatories, it became one of the most chilling developments. Yet, roughly 3 hours after the second auroral flash faded, the Solar Dynamics Observatory reported a clear reorientation in the jet stream being emitted from 3I Atlas. Previously, the object released symmetrical jets, short bursts of ionized material ejected at irregular angles, sometimes spinning off the tail, sometimes curving away from the sun. Erratic, shifting, natural. But now one jet went dead, straight locked into position and pointed, directly along Earth's sunline. Not near it, not vaguely, in our quadrant, perfectly aligned. It wasn't easy to detect. The first alert didn't come from a major agency, but from a high-resolution amateur observatory in Argentina, which noticed a sustained thrust feature in stacked exposures, overlay it with ephemeris data, and the conclusion snapped into focus. The jet's projection traced a straight path through the solar ecliptic, matching Earth's current orbital vector with near-zero angular drift. ESA's Solar and Heliospheric Observatory confirmed it quickly. Coronagraph images showed the jet cutting cleanly through the inner solar system, not spreading, not diffusing, holding. For many researchers, the tone changed immediately, because this wasn't just a jet, it was a directional act. Material, plasma, dust, something unknown emitted deliberately in one direction toward a moving target toward Earth through the sun's gravitational lensing path. Comets don't do this. They vent, they react to sunlight, they break apart, they don't target. Speculation ignited again. Some called it an alignment fluke, a byproduct of rotation and gravity, but simulations failed. The jet held too. Precisely its stabilization, too clean, too long, too efficient. Others feared something darker, that 3 Atlas wasn't merely awake. It was watching not with eyes, but with orientation, with geometry, with an intentional placement that felt almost mechanical. AVIB, contacted by multiple groups, reportedly offered a chilling assessment. This isn't random alignment, this is choreography, and the implications were staggering. If 3I Atlas had real-time awareness of Earth's sunline, it meant it could process positional vectors in 3-dimensional heliocentric space. That requires feedback, sensing, navigation, or something beyond what we assign to interstellar debris. The jet showed no variance over the next 2 observation cycles. Even as Earth continued along its orbit, the emission held its angle, suggesting the object either updated its vector in advance or tracked Earth's position in real time. Then came one more twist. Modeling the jet's reach with solar wind data showed the stream would not physically contact Earth. It would pass within millions of kilometers, but orientation alone was enough to function as symbol, as marker, not weapon, not communication. A gesture, a single sustained, unchanging line drawn between itself, the sun, and us, as if to say, "I know where you are. I choose to look there." And despite the intensity of the alignment, there was no radiation spike, no particle storm, no increase in space weather. The jet, visible in high-contrast imagery, carried minimal mass. This was not force, it was posture, and in deep space where distance usually protects us from intent, that deliberate line felt more intimate than anything yet recorded. 3I Atlas wasn't speaking, it was pointing, and, Earth was now directly in the line of sight. It began as a faint anomaly, a flicker along the outer limb of the Sun, captured in a routine scan by the Solar Dynamics Observatory. At first, it looked like a brief drop in ultraviolet intensity along the Palatus, the southeastern quadrant of the solar corona. Nothing dramatic, no flares, no spots, no bursts. But it didn't fade. The numbers kept drifting downward, not sharply, consistently, and only in one isolated sector, roughly 6 degrees wide, positioned precisely where 3 Atlas's aligned jet had been, aimed the night before. What made it so bizarre wasn't just that the corona was changing, but how it was changing. The solar corona is one of the most extreme environments in the system, burning at temperatures above 1,000,000 degrees, seething plasma, driven by magnetic chaos, unpredictable, wild, violent. Except now, it was cooling gradually and locally, like something had gently opened a valve, releasing heat, not by expelling it but by suppressing it. NASA's heliophysics teams first. Suspected calibration drift. Instruments age. After all. But cross-referenced data from ESA's solar orbiter showed the same story, the same region, the same drop, the same suppression pattern beginning shortly after the Earth. Sunline jet alignment from 3I Atlas temperature estimates fell nearly 7% below typical coronal values in that pocket, and the cooling zone held steady even as the rest of the Sun continued its chaotic flares and ejections. The question wasn't how much, but why. What could cause a precise segment of the corona measured in real time, from multiple orbital perspectives, to slip out of thermal equilibrium? And why that exact segment? Because when plotted geometrically, the affected slice matched the projected path of 3I Atlas's jet vector, creating a perfect linear overlay between object, solar jet, and solar response. A chill moved through the astrophysical community. Was 3I Atlas reflecting some exotic particle stream? Was its jet-bending magnetic structures, or was it draining something? Some theorized a process akin to magnetic reconnection but on an interstellar scale. Others explored even stranger ideas that the object might be drawing or redirecting solar energy through gravitational lensing or triggering localized magnetic dampening. But one thing remained clear: the Sun had never cooled like this. Not this way, not this shape, not this line. It wasn't an explosion, it wasn't a flare. It was the absence of both silence inside the most violent place in the solar system, and the phenomenon grew more eerie when coronagraph imaging isolated the cooler zone light scattering. Inside, it had dropped not only in heat but in turbulence. Solar wind streams appeared smoother in that sector, less chaotic, as if something were reducing random plasma motion like a hand, smoothing the surface of boiling water. This wasn't only cooling, this was control. And again, the vector pointed back to 3I Atlas, a vibe. In a closed-door conference, is said to have distilled it into a single line. Whatever that object is, it isn't afraid of the Sun. It's shaping it. Whether deliberate or incidental remained unclear, but from that moment on, one truth hovered behind every whispered conversation and recalibrated sensor. The Sun had blinked, not because of itself, but because something else was in the room, and Earth was next in line. Just after sunrise across Europe, the data feeds fell still. No more spectral surges, no more reoriented jets, no new pulses, no auroral flickers, no magnetic anomalies, just silence. The sky above Earth looked the same, but the rhythm was gone. For 72 hours, 3I Atlas had dominated every major Northern Hemisphere observatory. Its behavior escalated step by step, from dramatic tail loss to directed emissions, strange interactions with the Sun, alignments with no natural precedent. Each new event hinted at something larger, a rising pattern, a building crescendo. Analysts whispered of intentionality of choreography, of something we were meant to witness. And then, without warning, it all went still. At first, researchers suspected sensor glitches, dead telemetry packets, momentary blackouts. But redundant systems across NASA, ESA, and private agencies confirmed the same thing. 3. Atlas was no longer active, the aligned jet gone, the pulses silent, its brightness dimmed down toward background levels. Even the strange cooling arc in the solar corona began warming back. Up. The object hadn't vanished. It was still there, moving along, its projected heliocentric path drifting into its outbound phase. But everything that had made it feel intense, alive, had faded. No energy spikes, no decay signatures, no thermal bursts. It hadn't exploded, it hadn't disintegrated, it had simply stopped. And that was more unsettling than any burst or break, because if 3 Atlas had been following a sequence escalating in complexity over days and oriented in Earth's direction, then why stop? Why stop now? Some analysts believed it had completed its objective, that it had watched, scanned, measured, that it had finished whatever interaction it came here for. That Earth, the Sun, and the orbital geometry between them had been part of a brief, intentional observation window. Others suggested hibernation, that what we witnessed wasn't an end, but a pause, a temporary cease in visible activity before a transition toward the outer solar system, or beyond. A smaller group feared something darker, that it was now waiting, having sent its signals, drawn its lines, triggered reactions, and now holding position not from exhaustion but by design. Whatever theory you chose, what lingered was the emotional shift. For days, the global space community lived in heightened attention. Alerts every hour, constant cross-checking between observatories, a rising pulse behind every headline, and now only absence, an eerie void where activity had been like waking to realize the sound that kept you company all night has stopped. And you didn't notice when. Even amateur astronomers felt it. Online communities that had buzzed with live tracking data grew quiet. Enthusiasm softened. Scopes found nothing new to chase, no changing brightness, no new angles, only a dim object, sliding silently away from the sun. NASA removed priority status from its bulletins, updated its threat index to neutral. The Minor Planet Center logged position and moved on. But among those who followed 3 Atlas closely, who saw the alignments, the cooling corona, the directed jets, the magnetic taps, there was no relief. Only one question that wouldn't leave. Did it finish watching? Or is it just waiting? Because whatever intelligence, natural or not, had animated its strange behavior had gone quiet. And in that silence, Earth was left with only its reflection. No answers, no response, just the feeling that, for a moment, it had been seen, and then it stopped.